On a steep hillside near ancient Arles, the ruins of Barbegal preserve the outline of something far more ambitious than a village mill, a purpose-built industrial complex organized around 16 waterwheel positions. They were arranged in 8 parallel pairs, stepping down the slope so that water could do work repeatedly as it descended. The unusual feature is not simply the number of wheels. It is the arrangement, a cascade designed to turn one controlled supply of falling water into a sequence of mechanical operations. At each stage, the falling water supplied torque to a wheel. That rotation could then be redirected through wooden gearing and carried to a millstone, where the movement became the practical business of crushing grain. The complex therefore joined hydraulic engineering, power transmission, and food production in one tightly planned hillside system. But the surviving masonry does not hand us a complete operating manual. The wheels, gears, and wooden fittings must be understood through a combination of archaeological traces and engineering reconstruction. How did this cascade transmit useful power without wasting the energy at every step? And if Roman builders could coordinate a machine on this scale, why did water-powered industry remain an exception instead of becoming the foundation of a broader mechanical economy? Barbigal matters because those questions meet in one place, a ruined slope where infrastructure was arranged to behave like a factory. At Barbigal, the first evidence is not a surviving machine. It is the hillside itself. Near ancient Arles, the mill complex was cut into a slope so that water could arrive high, descend through the site, and reach a series of working positions below. Foundations and channels mark the intended arrangement, even though the wooden wheels, shafts, and most of the gearing have disappeared. The masonry establishes where water was meant to travel and where machinery once stood. It does not preserve every wheel dimension or show exactly how continuously the mill operated. The reconstructed plan identifies 16 wheel positions, arranged as 8 paired stations along the descent. Their regular spacing, channels, and shared water system point toward coordinated production rather than unrelated household mills. The site therefore provides a mechanical outline. A channel approaches a working level. A foundation provides a place for a wheel or mill assembly. Another route carries water onward. Wear and sediment patterns can help test whether some routes were active, although they cannot restore the missing timberwork with certainty. Engineers make that outline move by comparing channel geometry with the elevation of each stage, asking how water could enter and leave a wheel, and testing whether the proposed arrangement fits the surviving foundations. The water routes, wheel positions, and production sequence must work together. That is the responsible boundary between archaeological evidence and engineering reconstruction. The source of that controlled descent was not an isolated stream beside the mills. It was an industrial use of Roman water infrastructure. An aqueduct normally exists to transport water across a landscape, maintaining a carefully managed gradient so the supply can reach its destination. At Barbigal, a branch of that system could also provide something the destination itself needed, elevation that water had not yet spent. Think of the water arriving at the upper part of the site with a difference in height still available between its entry point and its eventual lower outlet. That vertical difference is the hydraulic head. The reconstructed drop across the mill complex is often placed at roughly 60 feet, or about 18 meters, but this is an estimate based on the surviving layout and proposed water levels, not a perfectly measured operating figure. Head is important because water raised above a lower level carries potential energy. For each unit of water, the available amount increases with its height above the point where that energy will be released. The aqueduct's transport function has therefore been extended into a power system. Instead of simply delivering water, The branch positions it so gravity can make the water descend through machinery. That does not mean the entire vertical difference became useful motion. Some energy would be lost through friction, leakage, turbulence, and imperfect control, and the actual result would depend on flow as well as height. The point is more precise than saying the Romans found a strong water source. They arranged a water source and a vertical profile so that falling water could perform repeated work. Seen from above, the aqueduct branch may look like infrastructure ending at a mill. Seen in section, it is a store of usable elevation being released down the slope. The challenge was then to divide that descent intelligently, so one broad supply could reach several working lines rather than rush through the site in a single uncontrolled channel. At the head of the mill complex, the water had to change from transport into distribution. A head race could carry the supply toward the first working level, where branches and flumes directed it toward separate wheel positions. The crucial task was not merely to split the stream into as many channels as possible. Each branch had to receive enough flow to do useful work, while the overall system preserved a controlled descent for the levels below. A schematic version looks simple. One channel divides, then divides again into parallel lines. In masonry, however, every division creates problems. If one branch is steeper, wider, smoother, or less obstructed than another, it may take more of the flow. A narrow passage can accelerate water and increase turbulence. A rough joint or damaged channel can leak it away. Debris could obstruct an inlet, while an uneven slope could cause water to pool where a steady delivery was needed. Those concerns make the channel dimensions and elevations significant even when the original wooden fittings are gone. A flume approaching a wheel had to guide water with enough control to strike the intended part of the machine. Its outlet then had to carry the spent water away without undermining the foundation or flooding the next work area. The channels were not passive gutters. Their shape determined how much water reached each wheel and how much head remained after the drop. The paired arrangement also imposed a balancing problem. Two neighboring wheel lines could draw from a common supply, but their inlets could not be treated as interchangeable if their elevations or resistances differed. A workable design would have needed some combination of carefully set channels, openings, and drops to keep the parallel routes broadly useful. That is an engineering requirement, not proof that the flow was perfectly equal at every moment. Most importantly, the branches had to preserve the logic of the cascade. Water could spend part of its available height at an upper station and still continue downward, provided the discharge was collected and redirected rather than allowed to scatter. Each flume was therefore part of two systems at once, a local delivery line for one wheel and a link in the descent feeding the next level. The head race made the complex a network, not a row of machines supplied independently from separate streams. The revealing feature appears when the layout is read downhill. Barbigal was not 16 wheels, each receiving its own complete water supply. It was 8 paired stations arranged in sequence, with water spending part of its available fall at one level before continuing to another. The cascade made the slope itself part of the machine. Within a pair, 2 wheel positions operated in parallel. They could draw from related branches and perform work at the same general stage. Down the hillside, however, the relationship changed. The water route was serial. After serving an upper pair, it descended toward the next pair, then the next, using the remaining elevation step by step. Parallel operation increased the number of working positions at one level. Serial descent allowed the same broad water supply to serve the complex repeatedly. A cutaway view makes the compromise visible. At the top, the water has the greatest available head, but only the first stations can use it. Lower stations depend on what survives the earlier drops. If an upper channel consumed too much flow, leaked badly, or discharged water beyond the next inlet, the lower wheels would lose capacity. If the designers held back too much head for the bottom, the upper wheels would be underused. Total output depended on balancing the whole slope rather than maximizing any single stage. That is why the number 16 can mislead. It describes wheel positions, not 16 independent sources of energy. The productive advantage came from coordinating pairs across a descending system. Each level had to be placed where a useful fall could be created, while its outlet remained recoverable for the next level. The masonry arrangement preserves that repeated rhythm of delivery, drop, and continuation, even though the precise wooden connections must be reconstructed. The result was an unusual hydraulic economy. Water did not perform all of its work at once and disappear. Its descent was organized into a chain of opportunities. The upper and lower stations were consequently tied together by design. Barbigal's scale came less from one gigantic wheel than from making many moderate working points cooperate along the same engineered fall. The type of wheel matters as much as the height of the fall. In an overshot wheel, water enters near the top and fills buckets or compartments around the rim. As that water descends, its weight acts at a distance from the axle. The wheel is not merely being pushed by a stream, it is being pulled around by a moving load. That is why a steep drop could be especially valuable at Barbigal. Set the same water volume and the same available head beside an undershot wheel. The undershot design places the wheel in the current, with water passing beneath it and striking paddles. Its main source of motion is the speed of that moving stream. It can work effectively where water is already flowing quickly, but much of the water's elevation remains unused unless the arrangement first converts that elevation into velocity. The overshot wheel makes a different bargain. It spends time filling, then lets gravity act through much of the wheel's descent. In favorable conditions, that extracts more of the water's potential energy than a simple paddle wheel below the same channel. But the advantage is not automatic. Water has to enter cleanly, fill the buckets without excessive splash, and remain contained long enough to produce torque. Gaps at the rim, leakage through the sides, poor bucket shape, friction in the axle, and a wheel turning too quickly could all reduce the useful result. That distinction is important for Barbigal. The reconstructed wheels were suited to falling water entering from above, not to a single fast current sweeping beneath them. Each stage therefore needed a workable balance between head, flow, wheel geometry, and discharge. An overshot wheel could take more energy from a given fall, but only if the carpenters and masons maintained the path that made the fall usable. Efficiency here is best treated as a range shaped by losses and by uncertainty about the missing wooden parts, not as one guaranteed percentage. The Cascade gained its power from gravity, but its performance depended on how carefully gravity was managed. A useful way to test the system is to stop looking at the wheel and begin with the water. The ideal hydraulic power is given by water density multiplied by gravity, flow rate, and head. In ordinary terms, more water per second increases the supply of energy. A greater vertical drop increases it as well. The relationship is simple. Power equals density times gravity times flow times head. Take an illustration, not a measurement of Barbigal. Suppose a channel delivered 1/10 of a cubic meter of water each second through an effective 18-meter fall. Multiplying 1,000 kilograms per cubic meter by roughly 9.8 meters per second squared by 0.1 and by 18 gives about 17.5 kilowatts of ideal hydraulic power. That is the energy available before the wheel, axle, bearings, gears, and millstone take their share. If the complete mechanical path delivered, for example, 60% of that ideal figure, the useful output would be about 10.5 kilowatts. The exact percentage is only an illustration. In the real complex, flow may have varied between levels, and losses would have accumulated through leakage, turbulence, rubbing surfaces, imperfect gear contact, and the milling process itself. The point of the calculation is to show why a reported output cannot be checked from the number of wheels alone. We need flow, head, operating time, and a defensible account of losses. The cascade also divided the available energy. Water reaching a lower station still carried usable head, but not necessarily the same quantity or quality of flow that entered above. At every stage, the system exchanged hydraulic energy for shaft work. That shaft work then appeared as torque and rotational speed. For a given power, a slower shaft can deliver more torque, while a faster shaft delivers less torque. The mill therefore needed not just spinning motion, but spinning motion with the right force at the stone. This is the practical test of the design. Water had to arrive in sufficient quantity, the wheels had to turn at a controllable rate, and the transmission had to preserve enough torque for useful grinding. Barbigal was managing an energy budget and a mechanical behavior at the same time. At one level of the slope, the two wheels made the arrangement useful in a very practical way. Each could power its own milling station or another nearby mechanical load, allowing work to proceed at 2 points instead of concentrating every task around one axle. The water was shared by position in the cascade, but the productive work could be distributed across separate takeoffs. That is a different strategy from building one enormous wheel. A giant wheel might concentrate power, but it would also demand a larger structure, heavier timbers, stronger bearings, and more exact control of the incoming channel. A failure in that single machine could stop the entire operation. Moderate wheels reduced the scale of individual components and made the system more divisible. One station could require attention while others remained available, although the surviving remains do not tell us how maintenance was scheduled in practice. Parallel wheels also helped turn water delivery into multiple milling opportunities. At a paired station, the flow could be divided between two wheel channels, and the resulting rotations could be taken to separate millstones. That increased capacity without requiring one shaft to carry every load or one wheel to absorb the entire fall. It also made the output of the complex easier to regulate. Individual stations could be slowed, stopped, or serviced without treating the whole hillside as one indivisible machine. The masonry proves the repeated paired lay out more securely than it proves the exact wooden connections, so the safest reconstruction is not 16 wheels sharing one continuous shaft. It is a sequence of paired working points, each with its own power takeoff, coordinated by the channels around it. The achievement lay in multiplying manageable machines while keeping them inside one hydraulic plan. The wheel and the millstone did not necessarily want to turn around the same axis. A wheel axle could run along the channel or across the building, while the millstone spindle needed to rise through the stone and rotate vertically. The transmission, therefore, had to redirect motion through roughly 90 degrees before the grain could be ground. The reconstructed solution is a pair of bevel gears. One gear sat on the wheel's axle, and its angled teeth engaged a second gear mounted on the upright spindle. Because the teeth met on sloping surfaces, rotation could pass around the corner. Horizontal motion became vertical motion, or the reverse, depending on the arrangement. This is the essential function of the gearbox. It changes direction first. It does not automatically determine how fast the spindle turns or how much torque it receives. That redirection demanded much more than two wooden discs placed near each other. The gear centers had to remain at the correct distance, their teeth had to meet evenly, and the shafts had to stay aligned under load. If the axle shifted, the teeth would press on one edge instead of sharing the force across their contact surfaces. The result could be rapid wear, vibration, or a jam. Bearings and supports therefore mattered as much as the visible gears, and some form of lubrication would have reduced rubbing where wood carried the load. The word wooden can make the transmission sound rough, but a working gear is a precision component even when it is made by a carpenter rather than cast in metal. Tooth spacing, diameter, grain direction, and the fit of the axle all affected whether rotation moved smoothly. Water could supply the energy, yet the gearbox decided whether that energy arrived at the millstone as usable motion. The exact dimensions and every connection are not preserved well enough to reconstruct the machine without qualification. Archaeological evidence gives the layout and supports the engineering interpretation. The missing timber requires comparison with known gearing principles and plausible working arrangements. Within those limits, the right-angle transmission explains how a wheel station could occupy one orientation while the grinding equipment occupied another. It turned a change in direction into a workable mechanical pathway. At the end of that right-angle transmission, the next problem was not simply to keep the shaft turning. It was to make the rotation strong and controlled enough to drive a millstone. One useful component in that conversion was the lantern pinion, a cage-like pinion built from a set of wooden rods held between circular plates. Instead of a solid wheel with projecting teeth, it presented rounded rods that could engage the teeth of a larger gear. That arrangement made the ratio visible. Suppose a small lantern pinion with 10 rods drove a larger gear with 20 teeth. If the small pinion turned once, the larger gear would turn roughly half a revolution. Speed would be reduced by about half, while the turning force or torque would be increased by about 2 times before friction, flexing, and other losses. The power is not multiplied, the machine is trading speed for force. In simplified terms, what is lost in rotational speed reappears as greater torque at the slower shaft. That trade mattered because a millstone does not reward maximum speed. A fast, lightly loaded shaft can slip, vibrate, overheat the working surfaces, or fail to grind grain evenly. The runner stone needs enough torque to maintain its motion while grain enters the gap between the stones. Its speed must remain compatible with the stone diameter, the pressure between the surfaces, and the quality of flour being produced. The lantern pinion also offered practical advantages. Its open cage could be made from rods that were individually replaced, and its shape could engage a large wooden gear without requiring a massive solid-toothed wheel. But the precise Barbigal dimensions are not preserved well enough to assign a certain ratio to every station. The archaeological remains support the presence and function of a geared transmission. The exact tooth counts belong to engineering reconstruction. What matters mechanically is the sequence. The water wheel supplied rotation, the bevel gears redirected it, and the lantern pinion and larger gear adjusted its speed and torque. By the time motion reached the millstone shaft, the system had converted falling water into a form that could do sustained grinding work. The final working interface was the millstone pair. Grain entered through the eye, the opening at the center of the upper runner stone, and spread outward through the narrow space between that stone and the stationary bedstone. The lower stone stayed fixed. The upper stone rotated, forcing the kernels through a moving surface where pressure, friction, and the patterned furrows broke them down and carried the meal toward the edge. This was not a simple spinning disc. The gap between the stones had to be adjusted closely enough to grind effectively without allowing the surfaces to strike. A wider setting could pass grain quickly but leave it coarser. A tighter setting increased the grinding action, but also raised friction, heat, and the risk of damaging the stones or spoiling the flour. The feed rate mattered as well. Too little grain wasted available motion. Too much could overload the runner and stall the shaft. That is why the earlier torque trade becomes practical here. The gearing had to deliver a steady turning force at a controlled speed, not merely transmit the wheel's motion. Stone diameter, surface condition, grain moisture, and the chosen gap would all affect the load. The same water supply could therefore produce different results depending on how the mill was adjusted and maintained. the internal sequence is reconstructed rather than preserved as a complete working machine. The masonry identifies the stations and supports, while missing timber, stone fittings, and feed arrangements must be inferred from milling practice and mechanical requirements. Even so, the principle is clear. Water power became shaft torque. Shaft torque kept the runner stone moving, and the moving stone converted that torque into repeated shearing and crushing of grain. Unlike a human or animal mill, the water source could provide motion for long periods without the power source itself tiring in the same way. That did not guarantee uninterrupted production, but it made a more stable rhythm possible whenever the channels, wheels, and gearing remained in working order. Now the headline output can be tested rather than simply repeated. A commonly cited reconstruction assigns the complex roughly 4.5 tons of flour per day. That is an estimated throughput, not a surviving Roman tally, so the useful question is what workload the figure implies. 4.5 tons spread across 24 hours equals about 187 kilograms per hour for the entire installation. If 16 wheel positions corresponded to 16 milling stations, the average would be only about 12 kilograms of flour per station per hour. If production was concentrated in fewer active stones, the demand on each working station would rise. Either way, dividing the total into hourly and per station loads makes the claim less dramatic and more testable. A power check begins with the hydraulic side. The available work depends on flow, head, and operating time, then falls through losses in the water channels, wheel, bearings, gears, and millstones. The reconstructed drop of roughly 60 feet could provide substantial power if enough water reached the wheels, but head alone does not establish the daily output. A small flow over a large fall and a large flow over the same fall are very different machines. The milling side introduces another filter. Flour output is not identical to grain input. Some material remains as bran or meal, some may be lost during handling, and moisture changes the mass being measured. Stone capacity also depends on the grain, the gap, the condition of the furrows, and how often a station is stopped for adjustment. A full day on paper may include pauses that a simple calculation ignores, so the 4.5 ton figure works best as a model-dependent estimate. It is plausible only if the assumed flow, wheel efficiency, transmission losses, number of active stones, milling rate, and operating hours fit together. A reconstruction that produces the number under ideal conditions would describe potential capacity. Regular production would require the water and machinery to support that rate repeatedly. The calculation therefore gives a scale for the complex while also showing exactly where uncertainty enters. Power was only one line in the operation. Grain still had to arrive, enter the stones at a manageable rate, and leave as a usable product. A working complex would need space or containers for incoming grain, routes for moving it to the individual stations, and chutes or hoppers that could feed the millstones without constant hand placement. At the other end, flour or meal had to be collected, screened or sorted according to the desired product, and placed into bags or other containers. Bran and coarser material had to be separated or removed. These tasks did not disappear because the stones were water-driven. They became the handling system surrounding the mechanical core. The machines also demanded regular attention. Flumes and channels could accumulate silt or suffer damage. Wheel surfaces and wooden teeth could wear. Bearings needed support and some form of lubrication, while millstones required dressing to restore their furrows and careful adjustment to keep the working gap even. A broken tooth or misaligned shaft could stop one station, and a failure in a shared water passage could affect several stations at once. The water itself was variable. Flooding could damage channels, drought could reduce the available flow, and debris could interrupt the supply. Even when the aqueduct delivered water, a stalled wheel or jammed gear would lower the day's total. That means the estimated 4.5 tons should not automatically be read as a guaranteed daily dispatch. It may represent calculated capacity, an intended operating level, or a debated reconstruction of regular production. The material flow picture is therefore more demanding than the wheel array alone suggests. Grain in, controlled water through the wheels, power through the shafts, flour and waste out, and maintenance constantly returning to the system. Barbigal's achievement lay not just in making water turn stones, but in coordinating all of those flows closely enough for the machinery to function as a production complex. 4.5 tons of flour sounds impressive, but its demographic meaning depends on what each person is assumed to consume. At roughly 20 kilograms of flour or grain per person per year, that daily output becomes enough for the food equivalent needs of about 80,000 people. That is the arithmetic behind the famous comparison, not a verified register of Barbigal's customers. Change the assumption and the scale changes immediately. 4.5 tons is 4,500 kilograms. Divided across 80,000 people, it provides about 56 grams per person per day. That could represent a modest allowance within a wider food supply, but it is nowhere near a complete daily staple ration. At roughly half a kilogram per person per day, the same output would cover closer to 9,000 people. The useful conclusion is not that every resident of Arles received flour from this hillside. It is that the mill complex operated at a scale large enough to matter to an urban and regional food system. A major city, a military presence, or buyers drawing grain from surrounding estates could absorb a high-volume milling service, especially when flour had to be produced more reliably than scattered hand mills could manage. So the 80,000 figure is best read as a demographic scale marker. It shows what the modeled capacity could represent under a particular allowance, while the lower comparison shows why capacity is not the same as direct daily supply. Barbigal was large enough to become significant beyond its own walls, but the numbers still describe a range of plausible uses rather than a proven distribution map. The masonry gives us a firm starting point. The hillside carries a stepped hydraulic arrangement. Channels descend through repeated wheel positions. The remains belong to an industrial installation rather than to an isolated domestic mill. Those features support the broad reconstruction of water being guided through multiple stations and used for repeated milling, but the stones do not preserve the whole machine. Exact wheel diameters, wooden shaft dimensions, gear tooth counts, leakage rates, and operating schedules have to be inferred or modeled. Even the amount of water available at different seasons is not simply written into the channels. The number of millstones that worked at one moment and the number of hours they ran remain more difficult questions than the surviving layout suggests. This is where an evidence board becomes useful. On one side are excavated features, the channels, the levels, the wheel locations, the building remains, and their relationship to the aqueduct system. On the other are engineering reconstructions, the missing wheels, the bevel gears, the lantern pinions, the likely stone arrangement, and calculations of power and output. The second side is not fiction, but it is not direct preservation either. Experimental models can test whether a proposed wheel and gear arrangement would turn, whether water could pass from one stage to the next, and whether the estimated production is mechanically plausible. A successful test shows that the reconstruction can work. It does not prove that the ancient builders used those exact dimensions or ran the mill on that exact schedule. That distinction makes the 4.5-ton estimate more useful, not less. It becomes a transparent result of stated assumptions rather than a falsely precise production record. Careful uncertainty separates what Barbigal demonstrates clearly, an integrated hydraulic milling complex, from what it only allows us to reconstruct. There is an economic reason why a machine this capable did not automatically transform every Roman workplace. If labor was available at low cost, the pressure to mechanize every task was weaker. People could carry grain, feed hoppers, clear flour, move sacks, repair channels, and perform other operations that machinery might otherwise reduce or reorganize. That did not make mechanization pointless. Barbegal could still be attractive because milling was a repetitive, high-volume bottleneck. One installation concentrated power where thousands of grinding motions were required, while human work remained essential before and after the stones. The larger obstacle was the scale of the investment. Barbegal required access to an engineered water supply, suitable land and elevation, carefully built channels, heavy masonry, timber components, skilled construction, and continuing maintenance of shafts, bearings, gears, and stones. That commitment made sense only where reliable grain demand and dependable water could support it. Slavery, however, was only one part of the calculation. Markets determined whether flour could be sold. Roads, waterways, and storage affected whether grain could reach the mill and flour could leave it. Institutions shaped who could command land, water, and capital. Geography determined whether falling water was available at all. A technically elegant design could fail economically if transport was expensive, demand was irregular, or seasonal flow was too uncertain. This is why labor-saving machinery should not be confused with a general desire to eliminate labor. An owner might mechanize the stage that limited output while retaining a labor-heavy agricultural, transport, and distribution network around it. Barbigal solved one demanding production problem at exceptional scale. It did not make the entire economy behave like a machine. Set beside a standalone rural watermill, Barbigal looks less like a different invention than a different level of coordination. A single mill can use a local stream to turn one wheel and drive one set of stones. Barbigal linked water control, repeated wheel stations, right-angle transmission, speed adjustment, and organized grain processing into one continuous installation. That integration multiplied the value of each component. The aqueduct supplied more than water. It placed water at a usable elevation. The cascade reused its descent. The gearing made the wheel's rotation suitable for the millstones. The buildings and channels kept material and power moving through a planned sequence. Remove any one of those connections and the system becomes smaller, slower, or impossible to operate as designed. Replication therefore required more than copying a gearbox. Another site needed a steep and reliable water route, enough construction capacity to shape it, investment to build and repair it, and a sustained market for the resulting flour. It also needed people who could maintain wooden machinery and interpret the changing behavior of water. A rural mill might be useful with one wheel and modest demand. A cascade of this scale needed several conditions to align at once. That is the crucial contrast. Technical capability can exist without technological diffusion. Roman builders could create an impressive mechanized bottleneck, yet the surrounding geography, economics, institutions, and demand determined whether anyone had reason to repeat it. Barbigal was not a missing step waiting to be copied everywhere. It was a systems achievement whose rarity came from the difficulty of making all its parts cooperate. Barbigal was not simply a row of water wheels. It was a complete energy and production system. An aqueduct branch brought water to the hillside, preserving a usable fall of roughly 60 feet. From there, the water descended through 16 reconstructed overshot wheel positions, arranged in 8 parallel pairs. Each wheel converted falling water into rotation, and each shaft carried that motion through right-angle bevel gearing and lantern pinions to a millstone. The result was not one spectacular machine doing everything, but many working stations cooperating along the same engineered slope. That distinction also puts the output estimate in its proper place. Around 4.5 tons of flour per day is an engineering reconstruction, not a perfectly measured production log. Even so, at that scale, the complex could represent a food equivalent supply for roughly 80,000 people, depending on the assumptions about operating time, grain, efficiency, and demand. The number matters less as a census than as evidence of what concentrated mechanical power could accomplish when water control, gearing, buildings, labor, and logistics were made to function together. Does Barbigal look more like the beginning of an industrial revolution or the most successful exception to Roman economic habits? Subscribe for future breakdowns that connect archaeological evidence to the gears, energy flows, labor systems, and production limits behind historical machines. The answer is both revealing and limited. Barbegal demonstrated that Roman engineers could assemble a sophisticated powered production line, but mechanical possibility alone did not create widespread industrial change. Replication still depended on the right terrain, dependable water, capital, maintenance, transport, and a market large enough to justify the effort. Barbigal was not a failed industrial revolution waiting for one missing invention. It was proof that Roman engineering could assemble sophisticated power systems when aqueducts, capital, labor, and demand aligned, while the surrounding socioeconomic system gave the wider empire little reason to reproduce that model everywhere.